Welcome to Brain Vision.
For this problem on the topic of conservation of energy, a small circular hoop with a given radius is placed flat on a floor. Then a particle with a given mass slides around the inside edge of the hoop when it is given an initial speed of 8 meters per second. Now, after a single revolution, the speed has dropped to 6 meters per second because of friction with the floor. We want to find the energy that is transformed from mechanical to internal in the system as a result of friction in one revolution, and we want to find the total number of revolutions that the particle makes before stopping. Now we'll assume the frictional force remains constant throughout the entire motion. Now we know the change in internal energy of the system, delta E subscript I and T, is obviously the change in kinetic energy of the particle. So as the particle loses kinetic energy and slows down, that energy is transformed into internal energy. And we know how to calculate the change in kinetic energy, so this is minus a half m into the change in the square of speed. So the final speed squared Vf squared minus the initial speed squared Vi squared. And so we can substitute our values since we have all this information. So that's minus a half times the mass of the particle, 0.4 kg, into Vf squared, which is 6 meters per second squared, minus the initial speed, 8 meters per second squared. And so calculating, we get this change in internal energy to be 5.6 joules. So that's the change in internal energy, which is due to a loss of kinetic energy. Now, in part B of this problem, we want to know the total number of revolutions that the particle can make before finally coming to rest. Now we know after n revolutions, the object will come to rest, and the final kinetic energy will be 0. So the change in internal energy, delta E, is equal to minus delta K, like we said before. And the frictional force, Fk, times the distance traveled, d, is the work done due to friction, and hence the change in internal energy, delta E. And this is the change in kinetic energy, which is minus 0, the final kinetic energy, minus the initial kinetic energy, Ki. And so this is equal to a half m Vi squared. So we can write this as mu k mg, which is the frictional force, times the distance the particle will travel, which is n revolutions, times the distance around one revolution, which is 2 pi r, where r is the radius of the loop, is then equal to a half m Vi squared. So we've replaced the frictional force K with the coefficient of kinetic friction mu K times the mass of the particle m times acceleration due to gravity g, and then replace the total distance the particle will travel by the number of revolutions n times the distance around one revolution, 2 pi r. So from here we can rearrange and find the number of revolutions n, and n is a half m Vi squared over the coefficient of kinetic friction mu K times mg, mg being the weight of the particle, times 2 pi r. And again, all of these values are known, so we can calculate the number of revolutions that the particle will make before coming to rest. So substituting our values into this, we get this to be a half, and we can see the masses cancel, into the initial speed, 8 meters per second, all squared, divided by the coefficient of kinetic friction, 0.152, times the acceleration due to gravity, 9.8 meters per square second, times 2 pi times the radius of the loop, which is 1.5 meters. So calculating, we get the number of revolutions before the particle comes to rest to be 2.28 revs.